and turbulence, and show you that arguments taken from equilibrium statistical mechanics, as we know in part from Krajgman, can actually tell you something about certain turbulence problems. I will also show you that there is a new way of defining d-dimensional turbulence where d is anything, not an integer at least, which is drastically different from the one that has been used so far in field theory and statistical mechanics, which is amenable not just to fancy theoretical expansion, but allows you to do that. This is very unstable. Sorry, but is amenable to actual number crunching numerical simulations. So this work, at least the part on d-dimensional turbulence, is done with the people I say. Okay, now let me try to go to the next. Yeah. Is there a pointer? Yes, one of them. The general question of whether equilibrium statistical mechanics has anything to do with turbulence has occupied many people. At first sight, they're quite different, because equilibrium statistical mechanics is concerned with conservative Hamiltonian dynamics, Gibbs states and the like, whereas turbulence, at least the way we understand it, is about dissipative and out of equilibrium systems. But, as most of you know, nevertheless, equilibrium statistical mechanics and Gibbs state did play a very important role in allowing Krajgman to discover the famous inverse cascade of two-dimensional turbulence. This is a not so high quality picture but the connection between the two areas of research goes actually back a little bit before Krajgman, just a few years, to work by T.D. Lee on Galerkin truncation of the Euler equation. So let me remind you of the setting of that. Here you have the Euler equation, no need incompressible Euler equation. For simplicity, let's assume periodic boundary condition. And it is sometimes convenient to write it in abstract form, lumping the nonlinear and the pressure term together into one quadratic term, which is denoted B of dV. That would be the same as this one, except it's written in this abstract notation. Then a Galerkin truncation is defined in the following way. There are hundreds of ways you can define it, but this is, in my opinion, the most compact. There is a projector. This P is a projector, which depends on a wave number, which we call K sub G, G for Galerkin. It is just a low-pass filter, which kills in Fourier space anything that has any Fourier amplitude that has a wave number greater than kg. So you put it in front of the nonlinear term, and you also do the same to the initial condition. The result is a finite dimensional dynamical system, because on the periodic boundary condition, the Fourier space is discrete, and if you don't allow wave numbers greater than some prescribed cutoff, you're left with a finite number of degrees of freedom. Now this system can be rewritten conveniently in coordinates which are vaguely related to real and imaginary parts of Fourier amplitudes as some quadratic system of ODEs. The dot now stands for d by dt. And what's interesting is that if you do this in a reasonably clever way, then you get a dynamical system which conserves the Liouville measure, I mean the volume in phase space. This is a summation over alpha. We have summations of sign missing. Maybe the projector isn't doing the right thing. I have a feeling there was a sigma here. Okay. Because it's a conservative dynamical system and finite dimensional, you can apply to it standard tools of statistical mechanics. In particular, you will have Gibbs states. It turns out these Gibbs states are particularly easy for this game because the conservation laws, at least the conservation laws, the linear and the quadratic conservation laws, survive this truncation. It is actually a completely trivial exercise to show that quadratic invariants survive the Galerkin truncation. So you know this, so there's no need to go into the. And therefore, the kind of Gibbs states that you can construct based on the conserved quadratic quantities, say the energy in 3 dimension and energy in entropy in 2 dimension, is something where the probability of a state is given by a Gibbs expression, some e to the minus some combination of the invariants, where the alpha, beta, and so on are Lagrange multiplier. Actually, alpha can be considered as a Lindbergh temperature also. If you do that, and TDD was the first to do it in '52, you obtain an apparently very boring result. You may, in 3 dimensions, you didn't do it in 2 dimensions. In 3 dimensions, you just get, of course, a computation of kinetic energy among all Fourier modes. And since the number of Fourier modes in a ball in Fourier space that has radius k goes sorry, which has a radius, I should say that again, and not try to, it's difficult to wave the 2 hands and the stick at the same time. Yeah. In Fourier, if you're interested in how many modes there are between wave number k and wave number k plus 1, in order to get the energy spectrum, that number is clearly proportional to k squared in 3 dimensions. It's the same scaling law as the area of the ball of radius k. And therefore, this equilibrium state discovered by Lee has a k-square spectrum. A k-square spectrum got almost everybody laughing at that time. Maybe TDD wasn't sufficiently famous yet for other discoveries. Although the same year he made another important discovery on understanding the mathematical nature of phase transitions. So everybody knew that the spectrum of real, genuine turbulence in 3 dimensions is either k to the minus pi-3 or something close to it. So that goes down, doesn't go up, it's totally different. But if you do the game in 2 dimensions, and Crichton was the first to do that in 2 dimensions in 1967, because there are 2 invariants, and because the volume element is now replaced by the circumference of the circle, it goes by k to the 1 now, then you get k over alpha plus beta k squared. And that goes down. And depending on what alpha and beta are, you can get all kinds of states. And Crichton observed that alpha does not have to be positive. There is a minimum wave number, let me assume it's unity, if you take a periodicity of 2 pi. Then the only constraint is that this should never become negative. But the minimum value this takes is beta times 1 squared, which is beta. So if alpha is slightly negative, but alpha plus beta stays positive, then you're safe.
Not on Zagreb? Krajina did it? Not on Zagreb? Always on Zagreb?
No. What happened is that these particular states, which you can reinterpret, because alpha can be seen as a temperature, you can reinterpret them as negative temperature states. I was about to say that it is close to, but not identical to, Onsager's negative temperature states, which were published in the 1949 paper of Onsager, but for a different problem. The problem of point vortices, which is also a finite dimensional dynamical system, but they are not in easy one-to-one correspondence. But it is not a complete coincidence that both admit negative temperatures. Yeah. Now, let me give you an idea of how one can use these states, which Krajina called absolute equilibria, to predict, where did I put my pen? Here. To predict inverse cascade, an inverse cascade in 2 dimensions. Because the argument, this is going to be an argument of Krajina slightly enlarged, revisited, and which allows then to extension to a new animal to be introduced in a moment, which we shall call d-dimensional turbulence. But let's first do it in 2 dimensions, because essentially the argument is the same. First, let us do the following naive game. Suppose we have a cascade which in turbulence jargon is local. Local is of course Fourier local, which involves where the energy transfer is dominated by interaction between comparable scales. We may, using this localness, say that the things that act on a given wave number are mostly in wave numbers that are not too different from it. Maybe they differ by some factor 2 or something of this kind, and therefore it is of interest to try to cut Fourier space into slices, say octave slices, because most of the interactions here will come from things within this octave and so on. And then you do something too drastic. You isolate these things. You prevent anything from flowing through there. Of course, within each band, if you have no force and no or negligible viscosity, you get a truncated Euler equation with a finite number of modes, which will equilibrate. And if you are in 3 dimensions, it will go to a k-square thing, even if it initially you put in a k to the minus 5/3 or something close to minus 5/3, it will rather quickly evolve to a k-square spectrum. What do I mean by rather quickly? It is easy to see that the only relevant characteristic time is what we all call the local eddy turnover time. So all these things equilibrate, and then you get this strange spectrum. But then you say, well, that's not correct. I can't isolate these bands from each other. So let's remove all these things and see what happens. Now, then there is an argument which I found 20 years ago, which I don't like, which is to say, well, if I remove them, this is higher than that, this is higher than that, etc. So obviously the energy will flow in the direction to compensate that. It will flow to the right here. There is a better argument, you will see in a moment. But that's compared to what one obtains in 2 dimensions. So let's begin with a k to the minus 5/3 range, and let each octave equilibrate. And that's a slightly more difficult exercise, because you have to find the correct alpha and beta Lagrange multipliers, such that the integral over the band of k over alpha plus beta k squared multiplied either by 1 if it's the energy or by k squared if it's the entropy takes the same value as the energy and entropy that you can trivially calculate from a k minus 5 third. So that's a little exercise which leads to a transcendental equation that can be easily solved numerically. And when you do that, and now this would look like a log. This is a log-log sketch. This is a true log-log. This is a true lin plot. So 1 octave from wave number 1 to wave number 2. The blue thing is a k minus 5 third. The red thing is the absolute equilibrium that has the same energy and entropy. And you see, it overshoots here by about 10% and here by 5%. Therefore, if I put this back into the sketch, greatly exaggerating, particularly in log-log, I mean, you wouldn't see it at all. So it is. Then again, you would say, aha, this time things are higher there than there, so that maybe by the same weird argument I gave before, the energy would flow to the left. Okay? There is a better argument, which was invented this year, which I'm going to show you here. These are supposed to be straight lines. I'm not a great drawer. That's a k minus 5 third. And now, again, in sketch mode, this is greatly exaggerated, etc. It goes on. Okay. Now, what I say, I just remove this guy. The thing between two neighboring bands. Then this whole thing will equilibrate. And I can then find there will be a new equilibrium established, which of course will have the same energy and entropy as the sum of the energy there and there, the entropy there and there. But then I can calculate how much energy there is here in the new state. I mean, the new state is, I don't know how to draw it. I'm drawing it arbitrarily. The new state, the new equilibrium, has the same total energy as we had before, but the energy in one of those bands has no reason to be what it was before, and actually you can then calculate how much energy is flowing from there to there, or the other way around, and you find it is indeed negative. There is a flux to lower wave numbers. This kind of argument is still, of course, not rigorous, but we prefer it to using closure. So actually, Crichton also at some point decided that it was counterproductive sociologically to invoke closure too much, because he hadn't been too successful with in selling his direct interaction approximation, and even some later products which did not have the same defects but which were formally complicated. And at some point in the mid-60s, he made great efforts, and this has been, I know it personally, but I also know it from Jack Herring, that he made great efforts to present things by arguments that were independent of closure, even when he first derived them by closure. So this is a somewhat similar effort to present a thermodynamic argument rather than a closure argument. So what you see here is that the k to the minus 5/3 range is very close to an absolute equilibrium. You suppose that you begin to suspect that there must be some hidden small parameter there. That 2 dimension is too close to absolute equilibrium for not to have some explanation. So, okay, let's now we begin something that isn't quite d-dimensional turbulence, but is getting there. It's the work of our, how should I say, chairperson, not chairman, chairperson, of our chairperson with other persons, Anna and Victor. They observed the following. Suppose we had some way of defining d-dimensional turbulence in which we would have the same invariance as in 2-dimensional turbulence, namely energy and entropy. But in which, in evaluating how many points there are in the ball of radius k, we would use the d-dimensional version, so that where we had previously k squared in 2 dimension and k squared in 3 dimension and k in 2 dimension, we would have now k to the d minus 1. Then we would, by the same kind of arguments I gave before, we would have a k to the d minus 1 over alpha plus beta k squared. Now, one special case, when alpha is 0, is the so-called entropy equiposition state. That corresponds exactly to having the same entropy in all Fourier modes. And that clearly has a k to the d minus 3 spectrum.
1/3. 1/3.
No. D dimension. K to the d minus 3. Then they ask, when does that coincide with k to the minus 5/3? And that's a very simple exercise, and you find it happens for d equal 4/3. So that by this kind of argument, if you're able to define d-dimensional turbulence and then give d the value 4/3, you then predict that k minus 5/3 is an equilibrium entropy equiposition state, and a Gaussian one, because these Gibbs states, being e to the minus something quadratic, are obviously Gaussian. So you get a Gaussian equilibrium state, and which, being Gaussian, has absolutely no flux whatsoever. Complete equilibrium, boring equilibrium. But if you're sufficiently close to 4/3 and 2 happens to be not so far from 4/3, then maybe you can understand why things in 2 dimensions are not too far from equilibrium. But then the question, of course, arises: can we make sense of such d-dimensional turbulence? And because this is not a Nobel lecture and so on. You're all my friends, even the chairman. I owe you the truth. Following the suggestion of the chairperson, sorry. Yeah. We wanted to define d-dimensional turbulence not for this reason at all, but just because many of you know that one is able to extend all kinds of physical problems from integer to fractal dimension. For example, it's been known for quite a long time that you can do diffusion on fractals. So we tried for a year or so to do hydrodynamics on fractals in X-space. And had we tried longer, perhaps we would have succeeded. It's not clear. It wasn't complete failure. Okay. And then because the Weizmann Institute is such an inspiring place, and furthermore it's not far from Israel. It became at some point clear that this could be done in Fourier space. Now let me show you how this is done in Fourier space. Okay. So now I will define d-dimensional turbulence, not just assume that it exists in some mysterious way. Okay. So this is taken from a paper which is in the hands of the usual nice or not so nice referees. So what's important is here we have the Navier-Stokes equation. Now this time it's the full Navier-Stokes equation. This is the nonlinear term of before, so that's and that is the viscous term. And now we shall do something which resembles Galerkin truncation, but it is not quite the same. First, we do a Fourier decomposition again, assuming periodicity, and then we don't kill the modes that have a wave number greater than some prescribed kg. We kill the mode in a random fashion, in a quenched random fashion, it will not change in time, in such a way that the number of modes that survive in a ball of radius k, instead of being k square in 2 dimensions, are k to the d. It's very easy to do that. You just select, for each mode, you select the probability of survival with the right dependence on the wave number, k, and then you produce a certain disorder of modes live and dead, and you keep that during the whole process. There is a little technical constraint that you have to make sure that Hermitian symmetry is preserved, so therefore if mode k survive, mode minus k must also survive. And of course there are hundreds of ways you can do this, and we were interested in doing it isotropically, so that the probability depends only on the radius of the curve. So that's d-dimensional turbulence, and PD is just the projector on the surviving modes. The same kind of proof that one uses to show that energy and entropy are conserved for the Galerkin truncated 2-dimensional equation also works here. So this time we recover.
On average. On average.
Huh?
On average.
No. Exactly.
Because you project.
No. Exactly conserved. Exactly. Deterministically conserved. Yeah, they're conserved. And we can do all the usual things, the Gibbs states and the whole thing. And with that, of course, with this version of d-dimensional turbulence, the argument of, I forgot to say that it was in 2002, of Itamar, Anna, and Victor, becomes kosher. And so that's how it is done. And let's have a look at it. That's just baby food. I mean, you start with the 2-dimensional Fourier space, which is just a square array. That's what mathematicians call z-squared. And then you have modes that are alive, modes that are dead. I think the red ones are alive. If you choose a dimension that's quite low, and much below 4/3, 0.9, then you see what you have here. But that's just to get some mental picture. Actually, it is maybe more interesting to show what you have in dimension 4/3. This looks like almost like cosmology, but it isn't. It is just a Fourier space with this kind of decimation. You see that there are many more modes near the center than at the periphery because of the you get a lot of modes killed out there. Now what's interesting is that this d-dimensional turbulence, by the way, now I must tell you that it's deliberately that the d is capitalized. As you know, when you do fractal dimensions, the tradition is to have a big D. In field theory and in condensed matter physics, there is an alternative way of extending certain problems from integer to non-integer dimension, which roughly is that you do some statistical problem or some ensemble problem, and you calculate correlation functions or partition function, whatnot, in integer dimension d, and then if you're lucky enough, for example, because you have a possibility of expanding your correlation function in Feynman graphs or something like that, and you look at the dependence on the dimension, if it's sufficiently simple, you can then extend it to arbitrary value d. That's a little d, and this kind of extension has also been done in turbulence for the first time by Migdal, I believe, and then I worked on it with R.V. Rose and Fournier and others. This little d-dimensional extension conserves entropy only in exactly 2 dimensions. Worse than that, you cannot even make sense of d less than 2, because you can show that this kind of extension energies become negative in dimension less than 2. This is perhaps why I dismissed a little bit too fast the 2002 paper of the chairperson and others. But of course, this is a totally different game. The field theoretical extension allows you to do maybe nice theory, and of course the famous Wilsonian theory of phase transition in dimension close to 4 is an illustrious example of this. But you can't do any simulation of this thing. Here we are working with the usual equation, the almost usual Fourier space. It's just that some modes are dead, and you can apply the full machinery, for example, of spectral simulation. And so this is why I have reminded you of the first developer of this, Steve Orsag, who left us earlier this year. So this can be done, and during the last year or so, a lot of simulations of this were done at the Weizmann, and the results do support the ideas that came from the 2002 work, namely that as we lower the dimension, now in the sense of capital D, we call it fractal, Fourier fractal decimation. As we lower the dimension, the inverse cascade of Kragman is still present, but the Kolmogorov constant, which is already fairly large in 2 dimensions, something which wasn't fully explained before, becomes larger and larger, and presumably blows up as you approach for the dimension 4/3. and it goes, you will see in a moment. Oh. Why is it not turning? Ah, yeah, here it is. Okay, here are some of the simulation results. So these are simulations that are not as monstrous as those done by, where is Profeta? I don't see him. He's hiding. Okay, there. You know, he and Ozakio have done monstrous simulations in 2 dimension, but as you decimate, the simulation become harder and harder, and you have to integrate extremely long time. So if we had aimed for 16,000 or 32,000 modes, the simulation, instead of taking up to a few months, would have taken maybe tens of years. So we had to stay around 3,000 squared to be able to do that. And what you see is the usual so-called compensated energy spectrum, which allows you to measure the Kolmogorov constant, for example, and also the flux. The flux, which is happily negative, and you can then look at their dependence on the dimension. And you may notice that this does not get very close to 4/3. It stops just a little above 1.5, because if you try approaching 4/3, where there is, which is a critical point, the numerics becomes really too hard. I mean, you have to be either clever or use massive computer resources. But you can see the trend. The trend is clearly that the Kolmogorov constant, which is about here in dimension 2, goes up, you see, by a huge factor as you lower the dimension. And the theoretical prediction is not just that there is an equilibrium state in dimension 4/3, but you can predict the dependence of the Kolmogorov constant on the dimension by these kinds of arguments, because you can then calculate everything by hand. You can also do it by closure. It gives the same result, namely that the Kolmogorov constant blows up as d minus 4/3 equal to the minus 2/3. That's actually strictly equivalent to the statement that if you have a k to the minus 5/3 spectrum with a constant unity in front, and you want to calculate the energy flux, which is supposed to be constant, k independent, but the value vanishes linearly with d minus 4/3. Once you have that, it is almost trivial to infer from this that the Kolmogorov constant behaves in this way. So that's roughly what we have done. And I should mention that there have been very interesting attempts involving shell models to do something perturbatively, taking advantage of the fact that after suitable modification, not necessary of the dimension of the parameters in the model, one can have also a coincidence between an equilibrium state and one that has something to do with either an entropy cascade or an energy cascade. I mean, I should mention the work of let's see, Eric, Guido, who else was Vulpiani was there, and others. That was around 94. And you have done it with, what is his name?
The Belgian.
Yes, the Belgian. Gilbert.
Gilbert.
Gilbert, yes. Okay. But actually doing a perturbation theory remains a significant challenge. I can tell you technically why. That will be my last comment. if you want to do a perturbation theory, near, say, for example, dimension 4/3, then first you have to understand the equilibrium state much better than you do. The single time, the statistical distribution is very easy. It's a Gaussian with a k-5/3 spectrum. But you need also the multiple time, for example, the two-time distribution, because that will control the response function. And that is a non-trivial problem. Getting one's hand on it, I mean, Marc-Étienne Brachet tried to get some partial information on such things, and he was able to get the correlation between, at equilibrium between the velocity and its second time derivative, or its somehow higher order time derivatives. But the two-time correlation function is a really tough one. So, and that's the principal obstacle to trying to develop a perturbation theory near dimension 4/3. And that's, of course, one can perhaps learn something from simulation, because numerical experiments in dimension 4/3 by spectral method or so should allow us to measure the multiple time correlation function, and then that will perhaps give us a hint as to how to develop the theory. But I think I have said enough.
Thank you. Thank you very much.
Mr.